Okay, in the first part of chapter 30, it's hard where the learning objective is, analyze the current as the physical properties of the medium. It's not going to be possible to say, here is the equation, no, this thing. But I can give you an idea of what I'm talking about here. I have some space of material. Now, I'm going to define the current, or in class discussion or in the textbook, we define the current as the change in charge over a change in time. So if I've got, for example, a wire. Now, that's going to be a very common example that we use because, we can put one down in front of us. It is easier to conceptualize and we can keep everything focused in one case. In the case of a wire, it is the movement of charge through an area over some time delta t. Now, this four-wire, not in every case, but in honestly most of the cases we're going to be working with, this motion of charge is going to be carried by electrons. Why? Because if we've got a metal, electrons have much less mass. The smallest nucleus is the nucleus of a hydrogen atom, a single proton. And that's got more than 1,800 times the mass of an electron. So if you have iron that's got 50 plus times that mass, then, and that will be locked in place with chemical bonds, then it's the electrons will be free to move. So if I've got a current moving in one direction through wires, and through many things we're going to deal with, not everything. I can come up with ways where different particles are carrying charge. Honestly, most of the things we're going to be working with here are electrons. Now, the idea that charge moved by little tiny particles or tiny quanta of charge moving through some others, what look like solid matter, goes back up to the 18th century. And as a matter of fact, the description of this direction, if I've got charge flowing through a wire, that means I have charge carriers moving through that wire. Are we moving through that? Which way are they moving? Benjamin Franklin had to basically flip a coin in his hand. Unfortunately, he flipped wrong. Which is why, for a current moving from left to right, the electrons moving through the wire are actually moving from right to left. That is why the electron has a negative charge. So we've got electrons moving through this wire. And the electron current, in terms of electrons per second, that's equal to, first off, it's proportional to the drift velocity of the electron. Now, this isn't a uniform number. We've got electrons that are going through, it's like, they're nuclei and they're interacting with the nuclei and slowing down. Sometimes one electron stops when another one gets knocked free. It's an average, but we've got these electrons moving with a certain overall drift velocity. Now, the greater the cross-sectional area, the easier it is to move. Imagine you are in class, class ends, and you are eager to get out. The wider the doors are, the more people can move through. Yes, it's a broken analogy. All analogies are broken at some level. I'm making it ridiculously broken to hopefully make that stand out. Then, you need some characteristic, the conduction electron density, that depends on the metal, or depends on the substance. Actually, let's say conducting substance, which again, for pretty much everything I can think of, is going to be what we think of as a metal. Now, I can also write this in terms of, okay, this is still, whoops, that looks like an eta. Since I'm going to be using etas at times when they are helpful, I'm going to make it very clear that's an n. Still depends on the material-specific substance. But I can look at the drift velocity in terms of the electric field. If I've got a current moving in this direction, then that's caused by that's being driven by an electric field. Established in that direction. And the stronger the electric field, the more quickly the electrons are going to flow. Balanced out by the charge to mass ratio of the electron, where E in this case is the elemental charge, the tiniest bit of electric charge that can exist, because the greater the charge, the greater the force on the electron by being in an electric field, the greater the mass, the lesser the acceleration. Because, hey, Newton's second law, and this is also constructed with a time frame tau, which has to do with the mean time between collisions. Now, also, times the cross-sectional area, and this depends on the metal, this depends on the geometry of what we are doing. Well, dealing with the flow of electrons is not something we're going to work with because electrons are tiny. This elemental charge E that's got a charge of 1.602 times 10 to the negative 19th coulombs. Very tiny. So if we're dealing with like noticeable movement of charge, that's going to be on the order of, hey, 10 to the 20th coulombs, and an electron current, 10 to the 20th is a ridiculous number. So let us define the current in terms of the motion of charge, in which the units are amperes or amps, where 1 amp is 1 coulomb per second. And that current is equal to the charge on the electron times the electron current. This first learning objective I'm going to have to perforce cover somewhat briefly.